This is a second module based on chapter 2 of your ebook by Cheng El. This module covers energy transfer and energy analysis. In module 1, you have been introduced to the first law of thermodynamics, which states that energy can only change forms. It cannot be created or destroyed. But what about this equation? Some of you may have seen it before. It was developed by Albert Einstein. But from the equation, it does seem that energy is equal to mass. Well, mass is a form of energy. That is what I'm going to say now, but it requires a much amount of energy to apply this equation. Now, in module 1, we've been introduced to the two important types of thermodynamic systems for analysis: closed system and open system. So energy can be transferred to or from a closed system, that means crossing the boundaries of the closed system, into distinct forms, either by heat or by work or both. Whereas for an open system, what we call control volume, energy can enter or leave the control volume in the form of heat or work or mass flow, or all of them at the same time, because a mass flow can enter and leave an open system or control volume. For kinetic energy and potential energy, you know this way before. Yes, kinetic energy is the result of a motion of the system relative to some reference frame, as given here. And potential energy is due to the elevation in a gravitational field. Now, of course, during our thermodynamic analysis, there are magnetic, electric, and surface tension effects, but they are insignificant. And in our thermodynamics analysis, we generally ignore them. Let's go back to energy of the system. So, energy of the system consists of the contribution by the internal energy, kinetic energy of the system, and potential energy of the system in kilojoule. If it's in kilojoule per kilogram, the symbol used is lowercase. Most closed systems are stationary during a process. Thus, we have the change in kinetic energy is 0, and if the elevation is negligible, the change in potential energy is also 0. For control volumes, we have a continuous motion of fluid entering and leaving the system. So you need to know about the mass flow rate instead of just mass, control mass in a closed system. So for mass flow rate in kilogram per second, if you know the density or the volumetric flow rate or the cross-sectional area of the flow and the average velocity, you may get the mass flow rate. Internal energy U. In module 1, I stated that you do not have to know the degree or how the microscopic forms of energy contribute towards U, but you do need to know what they are. So for the energy that contributes towards internal energy, there are sensible energy, which is due to the translational motion of the molecules. There is molecular rotation, molecular vibration, electron translation, electron spin, and nuclear spin. And there's latent energy, chemical energy, nuclear energy. All these 4 types of energy contributes towards the internal energy U. Increase in any of these energy or sum of all, in terms of activities, will increase the value of U. So the forms of energy not stored in the system, like the kinetic energy, potential energy, and internal energy, are heat and work, because they are not stored in the system. They are energy in transition. Heat is caused by a temperature difference. Whenever you have a temperature difference between the system and its surrounding or within the system, then you have heat transfer. Anything that involves energy interaction, which is not due to temperature difference, is called work. So for a closed system, the only way the energy of the system E can change is through Q or W. That means if you have, let's say if Q and W are both 0, then the delta E will be 0, which means there's no change in energy. Now for an open system, the energy of the system can also be changed with mass entering and leaving that control volume. So For a perfectly insulated system, we normally assume is perfect, and so heat interaction at the boundary is 0. So the only way your energy of the system can change is through work interaction. Yes. Now, heat transfer, Q, can occur through 3 mechanisms: conduction, convection, and radiation, all at the same time or a combination of these 3. Yeah. So, both Q and W have directions and magnitude. So we say that if there are 5 kilojoules of heat entering the system, this is -5. Or if it's -5, we say 5 kilojoules is leaving the system. Yeah? Sorry, entering the system. So if it's leaving the system, it's positive. While work done on a system is negative, work done by the system is positive. Yeah? So how to remember this? Normally we say what is desirable is positive. Like, you do not like heat to enter the system, so we call it negative. If it leaves the system, it's desirable, it's positive. Just like the work done by the system is desirable, so it's positive. Work done on a system is negative. So schematically represented here. Yeah. Now, if the direction of Q or W is not known, you can make an assumption, like make a negative sign, and if you have the opposite sign from the initial assumption, then that means your direction is wrong. Yeah. Some characteristics of Q and W here, they are boundary phenomena. That means they occur at the boundary. At the end of the process, they are no more. You see, system possess energy but not heat or work. Yeah, they are associated with a process, not a state. Unlike properties, heat or work has no meaning at the state. And both are path function, if you're familiar with your first year calculus class. Yeah, so path function here, the Kronecker delta. So we do not use the full delta here. So the change in properties, on the other hand, we have the delta here, which only depends on the end state. So if you look here for process A, process B, for the change of properties from state 1 to state 2, regardless of process A, B, or C, the change is still the same. But for Q and W, it depends on whether you go through the red line, green line, or any other line that connects 1 and 2, their values may be different. So you can check out examples 2.3 up to 2.6. There are other forms of work. We have talked about heat, yeah, Q. So for work, there are many variations of work. There's electrical work. There is also mechanical forms of work, yeah, where it's a motion over distance. We have shaft work, we have spring work, elastic work, surface, and other forms of work. So when you go back to this equation, energy change of the system, Q is only heat transfer at the boundary, one form. But W, you have to consider all these forms of energy if they occur at the boundary, right? And you add them all up, and they are represented by the total W. Okay. So for the expression delta E from state 1 to state 2, for a closed system here, I would like you to think what happens if either Q12 or W12 is 0. So what happens if this is 0 or this is 0 or both are 0? Yeah. What happens for a stationary system? So you look at this. For a stationary system, kinetic energy is 0. So the change is 0. Yeah. What about the delta AU? Yeah. If a stationary system, what happens to the change in internal energy? Yeah. What happens when the system undergoes a cycle? The final state is back at state 1. Yeah. So this looks like a simple equation, but I would like you to think about the effect of each of these terms on the delta E from process from state 1 to state 2, one process, two processes, or even a cycle. Yeah. So for a control mass, because mass is always entering and leaving control volume, the change in energy is normally determined in terms of rate. Yeah. So here we have kilowatt instead of just kilojoule. And the performance, yeah, for any system, thermodynamic system, is based on the desired output divided by the required input. So that is for module 2 based on chapter 2 of your ebook.